We began our day with a global perspective on water issues from Brian Richter. Now we're going to narrow the focus a bit, and joining us today to address water issues specific to North Carolina is Dr. Kenneth Reckow. I had the opportunity to work with Ken when he was director of the North Carolina Water Resources Research Institute based here on campus. For I think, Ken, about an 8-year period of time, you were Water Resources Director. Dr. Reckow is an emeritus professor at Duke University in the Nicholas School of the Environment and the Department of Civil and Environmental Engineering at Duke's Pratt School of Engineering. He has been involved in issues of water quality his entire career and has served and continues to serve on many national and state level working groups to solve the problems of excess nutrients in our water. Please welcome Dr. Kenneth Reckow.
Thank you, Wayne. It takes me a little while getting over here and up the stairs. 3 weeks ago at this time, I was in Duke Hospital getting knee replacement. So it's nice to be able to walk again. It's also nice to be back here. As Wayne mentioned, I was on an 8-year basis from 96 to 04. I was director of the University of North Carolina Water Resources Research Institute, which is housed here at NC State. So 3 days a week for those 8 years, I came over here, and 2 days a week I had my reduced responsibilities at Duke. But the WRI position was terrific from my perspective. It gave me the opportunity to work with university faculty and graduate students primarily, but also the state agencies to help fund science that was supportive of informing decision-making on water quality and water quantity. So in doing that, I got to know many of the water researchers in North Carolina, and particularly at NC State. And it's nice to be back to see Wayne. Mike Williams is here, and Mike and I got to know each other from our commonality in research, but also because we had a running group of Weezers and Geezers faculty at NC State, and we would meet at the field every day at 11 a.m. and go through a grueling workout. It was camaraderie, it was competition. I kept hearing all these nasty things about Duke basketball, which of course were all untrue. But it was great fun. So again, it's great to be here, back to a place that I spent 8 years and really enjoyed. Okay, I'm going to talk about North Carolina water issues. Brian talked to a large degree about water quantity. I'm going to talk mainly about water quality. And what I'm going to talk about, see if I got this down, is water quality management, past, present, and future. And there are a few things that I will particularly emphasize in my early remarks concerning the water quality standards that we have right now and that evolve slowly, but they really are the foundation of our water quality management process. And they largely come, and this is fairly recent since the Clean Water Act 1972, they largely come from the federal government, but it's the state's responsibility to make many of the decisions and to do much of the regulations. And only when the states fail will an EPA region begin to be heavy-handed and take over some of the management. So I want you to understand how are standards established, the things that regulate our water quality. And you might think cost-benefit analysis would be utilized, although I suspect some of you think, what value can you put on a human life? And should we be thinking cost-benefit in setting standards? And what you will see is that implicit in any standards is the value of a statistical life. Okay, for drinking water standards, I'm going to talk about that first. And an interesting question that I will address is at what point from the reservoir to tap are drinking water standards assessed? Where are they assessed? And how do we know that the water from the kitchen tap is actually meeting the drinking water standards, which suggests that maybe then, the municipalities don't come in and test our meeting the standards actually at the tap, which is true. And how are drinking water standards assessed for private wells? There's a real difference in how we regulate in North Carolina drinking water quality in municipalities or with public water supplies versus our private wells. Okay, so after I talk a little bit about how we've effectively over years, over really the past century, regulated and maintained high-quality drinking water, I'm going to talk about ambient water quality. And ambient refers to the water quality in lakes, reservoirs, streams, estuaries. And I'm actually going to give a case study on the Neuse estuary that I was involved in when I was Water Resources Research Institute Director, and involved the faculty from many of the universities in North Carolina. So ambient water is the surface water, and it protects certain uses of the surface water, and including being a raw water supply for drinking water. One of the things we will discuss is how are ambient water quality standards expressed, and how is compliance of the standards assessed. This is an interesting issue, not only for the public, but for me as a scientist, particularly interested in how we use science to inform decisions under scientific uncertainty. Okay, let's first go through some slides talking about or describing drinking water protection. And I'm sure many of you are aware of at least some of this. A couple hundred years ago, we really didn't have a good idea. Most of the public did not have, and anyone involved in a governance or decision-making really didn't know how the plague and other major, what we now know as microorganism-caused illnesses happened. A miasma from the air, perhaps. By 1854, the cholera epidemic in London was linked to a pump at Broad Street. So beginning to make a connection, in this case, to something in the water. And then with Pasteur in the 1880s, his germ theory of disease was really catching on and making people aware of this. This is where a number of diseases, this is the cause of many of the diseases, something in the water. We have typhoid breakout in Lawrence, Massachusetts, 1887, cholera in the 1890s. And then in 1908, Jersey City, New Jersey was the first community to disinfect water with chlorine. So we took that knowledge over those 50 years or so and translated it into a workable approach for protecting human beings from microorganisms, recognizing the disinfectant power of chlorine. So that's just a little over 100 years ago, and that was occurring at the municipal level. And what we find in both drinking water and in wastewater treatment, which I'll look at subsequently, up until fairly recently, really the 1970s, it was the municipalities that were providing the drinking water treatment plants, the filtration and disinfection, in this particular case, or the wastewater treatment plants. And there was a big debate in the United States in the early 1900s, which is more important, treating the raw water to make it safe for drinking, or treating the wastewater before it's discharged into the nearby stream. The drinking water tended to win, and one of the arguments that was made was dilution is the solution to pollution. And basically what that's saying, and this works for sparsely populated areas, is you can discharge either untreated or partially treated wastewater into a stream, and the natural processes will allow the assimilation of that waste. And if there's no dangers of human intake downstream for a while, and if the populations aren't too great, that worked. Clearly it does not work in our country and in much of the world now, but that was the way the engineers argued for minimal wastewater treatment at the time, that really the receiving stream, if indeed it was a stream, was an extension of the wastewater treatment plant. Okay, so we see the cities constructing and the drinking water treatment and disinfection with chlorine. Okay, now we begin to see the federal government. When the federal government gets involved in something like this, as I mentioned before, say EPA, which is the real major entity at the federal level, they establish, let's say, regulations or requirements that the states have to adopt. So it's, while EPA has been doing much of this regulatory work and the mandates for setting standards, it's really the state's responsibilities to take that and work with it. So North Carolina, and now of course it's DEQ, they have the primary responsibility of carrying out the protection of our drinking water and our ambient water. So if we look though back 100 years ago, we see the first federal standards in 1914, mainly for interstate waters. And that notion of regulating interstate waters as opposed to within state waters was something that continued through perhaps the first half of the 20th century. The Public Health Service got involved. Makes sense that the Public Health Service would get involved in setting drinking water standards. And in 1974, the Federal Safe Drinking Water Act was passed, and this was an early recognition of a number of carcinogens in water. And these carcinogens could be synthetic organics, which have just exploded in number, as you guys know, over the past, say, 30, 40, 50 years. And many of them being found in waters at the very end of a large river, say like New Orleans. So with that knowledge, we have the first interim U.S. drinking water standards set in 1975. So this is really the first time we had regulations for drinking water in the U.S., again, set at the federal level, but implemented at the state level. And we also have these synthetic organic chemicals. Often these are carbon-based chemicals that have been wonderful in many aspects of our life, but can have this externality effect of being harmful in the environment, either to wildlife or to humans. So prior to this time, the drinking water standards, or many of the drinking water standards, were just regulating chemicals in the water, metals, let's say, or taste and odor chemicals that were more of concern for aesthetic purposes as opposed to human health purposes. So here's a transition in the mid-70s to recognizing that human health was what we should be more focused on protecting. So we see we have the inorganic chemicals regulated, turbidity, and then we have an indicator organism for bacteria, viruses, microorganisms. And we have indicator organisms like fecal coliform, total coliform, E. coli. And the reason those are used as indicators of the possible presence of pathogenic microorganisms is because there are so many possible pathogenic organisms that what we have adopted in the United States, and indeed everywhere around the world, is we have an indicator organism. And this is a major challenge for our science even today, and certainly then. What is the relationship between, let's say, total coliform and the pathogenic microorganisms that we really are concerned about? And the science is rather shaky in that regard. In some cases, there's a pretty good relationship, but in too many cases, alarmingly, the relationship is not very good. But the alternative is one that is really cost prohibitive, and that is identifying the pathogenic organisms that you might expect to find, let's say, in a raw water supply, let's say Falls Reservoir for Raleigh, and testing for all of those. So we rely on the indicator organism. And that, here we see it in 1975, and even I was involved in a project in Hawaii last year looking at a landfill serving Honolulu, and they were interested in whether or not a waste management firm had discharged sewage sludge into the landfill illegally. And the real challenge there was the indicator organism. And the challenge of the indicator organism was it's found in sewage sludge, but it also is found in the soils of Hawaii. So how much information can you get in that particular study when you're looking at the indicator organism, which is to be an indicator of the presence of pathogens from the sludge, and yet you have this contamination, if you will, of the soil. Okay, Safe Drinking Water Act in 1986. And this is where we begin to look at and focus on the toxic chemicals, particularly all of the synthetic organic chemicals that our chemical manufacturers are making throughout the world, and they make them because they're very helpful for our life, but there is this obviously a concern here. And what was found in just monitoring water systems is that many water systems have at least trace concentrations of these synthetic organics. So what was done is that Congress required that initially in 86 that 83 of these contaminants were identified, these synthetic organics, for standards development. And I'll show you in a moment how the standards are developed. And filtration of surface water supplies was mandated for most public water utilities. And this is interesting. EPA is to consider adding 5 new drinking water standards every 5 years. So currently the list is a little over 100 chemicals that, let's say, the city of Durham, city of Raleigh, and all the municipalities in North Carolina that have public water supplies, as well as the rest of the U.S., they have to monitor for, and they have to issue reports to us as the public on a regular basis as to what they're finding, if they have some non-compliance, and what they're generally finding. In most cases, they're doing very well. They're doing very well. Interesting that there's a treatment process, activated carbon, granular activated carbon, that is extremely effective at removing the synthetic organics. And yet the cost is such that while EPA looked into mandating that as a treatment process, ultimately it didn't happen, but some communities do have activated carbon, and probably maybe a number of you have these on filters under the sink or in Brita water filters or something like that, activated carbon. Interesting thing about activated carbon is it works really well with these synthetic organics, but it's working for a lot of contaminants that we really don't regulate and don't know. So interestingly, EPA said this is a good approach, and it may protect us from things that we're currently not regulating, but maybe down the road in the future we will regulate. But because of the cost, it's not something that is routinely used in drinking water treatment plants. EPA sets the standards. They prioritize the contaminants. They have a health goal based on risk, and I'll show you a little bit that shortly. They set the legal limit for the contaminant, and the states are mandated to adopt the EPA recommended standards. And that's for public water supplies. I haven't said anything yet about wells. Okay, let me just quickly run through this. I don't want to go into much detail on this. But this is typically what happens in setting standards. You have mainly animal studies for a contaminant that EPA decides we want to regulate, let's say over the next 5 years. Very rarely human exposures, and obviously they're not running experiments on humans if they have some accidental exposure information from humans. That's what they could use. So what they do after having lab studies on laboratory mammals or rats, they convert what they consider to be a safe level for mammals to a human safe level. And I'm not going to go into the details again, but I just want you to know how this works. They adjust that level for the average man of 70 kilograms. And notice this isn't for the immunocompromised individuals, for the average healthy, roughly 150-pound person. And that's interesting because in other sectors we do have regulations that are set for more sensitive members of the population, but not here. And then the standard is set based on human behavior assumptions, one of which is that 20% of the substance is ingested through drinking water. In many cases with chemicals that are in the water that volatilize when the water is hot, let's say in our shower, a certain amount can come through the skin. And the other assumption, average man drinks 2 liters of water per day. So factoring that in, that's the basis for setting the standards. And it may leave a number of you kind of uneasy about our drinking water standards, but on the other hand, this is a difficult process, and there are obviously decisions there that have been accepted that some of you may disagree with, like the average man being the subject of interest. Okay, drinking water, a few final issues. Chlorination was the initial disinfectant we saw initiated over 100 years ago. There are other disinfections. One of the more common one is ozone. The advantage of the chlorine as a disinfectant, which is what we have in most of the cities here in North Carolina, is that the engineers from the drinking water, the municipal drinking water system, can go out into the distribution system and test for what's called the chlorine residual. That chlorine residual indicates that there's still some disinfectant power in the distribution system. Whereas you can't do that with ozone. So that's what a number of drinking water engineers like. The disadvantage is that chlorination of some of the chemicals can lead to triomethanes, for example, which are regulated in the drinking water standard. So communities have to look at it. Now Raleigh and Durham are among the many who look at this. Having a certain type of chlorination or maintaining a level such that you have the disinfection power out in the distribution system, but you're not elevating the trihalometane levels so they exceed the water quality, drinking water standard. Private wells, those are regulated with county health departments here in North Carolina. And the main thing they look at are bacterial levels. So all the 100-plus contaminants that are regulated in the public water supplies are not looked at by the county health departments. Major reason is just be way too costly. So if you have a private well, the county will test it for bacteria, and you can spend the $1,000 or so to have it tested for all the others if you choose to. Location is obviously going to be an extremely important issue for protection of the private wells and the nature of the groundwater. Okay, water distribution systems, I just want to say something quickly about that. You can have what's called bacterial regrowth in the water distribution systems, and that I know where we live in Durham, for example, we're at the end of a line in a sparsely populated area, and the water can spend as much as a week, really, in the distribution system from the treatment plant to our tap. And in that time, things can happen, bacterial regrowth predominantly. So that has to be looked at periodically. And you may see in your municipality that someone's come out and opened up the fire hydrant. And a major reason for that is to flush out the water, flush out the system, and get rid of that bacterial regrowth. Okay, switching subjects. Now talk about ambient water and a focus on water and wastewater. Interestingly, with regards to our water and wastewater systems in the cities, we think of those as mainly serving domestic waste and maybe some small industrial waste. In fact, when they started, they were there for stormwater. And here you see the stormwater. Basically, there was a concern for centuries with a major storm and all the human waste and domestic waste just being thrown out the window. The desire was to get that stuff out of the congested areas as quickly as possible, and that was with these storm drains you see right here. And even up until 150 years ago, many of the older areas in the United States had combined stormwater wastewater systems, and then there was a real push to separate those systems. So newer systems have stormwater that isn't necessarily a collective system and a separate domestic and municipal wastewater system. Okay, let's see what goes on with regards to the history, the past of ambient water and mainly wastewater. Refuse Act of 1899. This was an act passed to improve navigation, and interestingly, it had a provision that any discharger of waste into a navigable water, I guess, had to get a permit to pollute. And that just created chaos because they had nothing, no one to keep those going. But interestingly, that permit to pollute is what we have right now under the NPDES system. I'll talk about in a moment. 1948 Water Pollution Control Act. That's really the first act. Everything else we've had up to 72 in the 80s is an amendment to that. That was written by those in Congress who didn't want strong pollution controls. And so it's not an act that was written by the water quality protection people. Then there were amendments in 56 and 65, and then we have the really groundbreaking act of the 72 Clean Water Act. Okay, and this is the one we're really operating under now with amendments. Restore the chemical, physical, and biological integrity of the nation's waters. Eliminate all pollutant discharge into the nation's waterways by 1985. Couple things there. One is that much of that, the nation's waters were thought to be navigable waters. And probably many of you have seen the issues of waters of the U.S. that Congress has been debating to expand the waters beyond just navigable waters. If we have time or questions, I can offer a few thoughts on that after I finish my prepared remarks. But these admirable goals have, unfortunately, put us in a situation where we have, in the environmental euphoria of the 1970s, I think, have established water quality standards and criteria that are unattainable. And that's put us in kind of a bind. And the one I will point to right now is the water quality criterion for Falls Lake, 40 micrograms per liter chlorophyll, which is leading to, right now at least, now maybe it'll change, a 77% reduction in phosphorus input. There's no way you can attain 77% reduction in phosphorus input without putting all the water flowing into Falls Lake into a wastewater treatment plant. That's not going to happen. So unfortunately, we have a goal right now that really we cannot meet and is leading to a lot of controversy that might be eliminated with other approaches. And I can get into that later in question and answer. Okay, key provisions. EPA did a terrific job with wastewater treatment plant construction grants. Big success in many ways of the Clean Water Act of 72 was the mammoth investment at the federal level and also at the state and local level of improved wastewater treatment plant. That was huge. They didn't meet the schedule of time, but it improved water quality dramatically to the point now where we are looking more at water quality standards, which were established in the 70s and 80s and even currently, because we've done so well with the wastewater treatment plants, we need to look at other things, notably non-point sources of pollution, to improve water quality and achieve compliance with the standards. And there you see the NPDES permit, National Pollutant Discharge Elimination System, which was probably the idea from the 1899 Refuse and Harbors Act. Okay, what I'd like to do now is talk a little bit about a study I was involved in when I was the Water Institute director here at NC State. First of all, let me note that we have, I believe it's 16 river basins, or portions of river basins in North Carolina. We have 3 really big ones you can see flowing into the coast. And much of ambient water quality management in North Carolina now through the Division of Environmental Quality, or Department of Environmental Quality, is on a river basin by river basin approach. Rotating basins. Every 5 years, a basin gets visited by the scientists to look at how things are going and look for things that need to be changed. Okay, so with the water quality standards that are set and are really now the focus of ambient water quality management in North Carolina and throughout the U.S., we have the standards, and the important things are the designated use, which may be a simple narrative statement like cold water fisheries or fishable and swimmables, or body contact recreation or boating, things like that, kind of vague. And then we have something that the scientists can measure, let's say like chlorophyll A, a measure of algal density, that is a surrogate for whether or not that designated use is being met. So you'd like to have a really clear connection between the criterion and the narrative designated use. But here, it calls up the notion of an indicator. But that's the practical nature. We can't go out and survey people for all the water bodies and say, is this satisfactory from the designated uses perspective? And so if a water body is found to be out of compliance with regards to the criterion, then it calls for a TMDL, total maximum daily load. That is, you need to find the culprit pollutant and determine what reduction in that pollutant is necessary in order to achieve compliance with the criterion. So here it is, the total maximum daily load. So this is really the program that is governing so much of ambient water quality management. In 2000, I chaired the National Academy of Sciences review of this program and got a really good picture as to how it's being handled nationwide. And it's very well, it's a good program here in North Carolina. For the most part, North Carolina is doing very well with this program. So I'm going to look at the Neuse estuary just quickly. Study that we worked on back in the 1990s and the early 2000s. You can see the Neuse River Basin and the estuary. We had in the Neuse River, at least, some really dramatic algal blooms. This is from the Raleigh News and Observer. They had some nice drawings. This is showing the estuary and some of the water quality problems, which included low dissolved oxygen, which was a key element in fish kills, and also violation of the dissolved oxygen criterion and the chlorophyll criterion. So we had what was called the Neuse Modeling and Monitoring Study, or Neuse ModMon, that looked at the relationships among these variables and what might be the reduction in the culprit pollutant, which was deemed to be nitrogen, to achieve compliance with the chlorophyll criterion. And as this was going on early years, there was a lot of controversy. Again, News and Observer. The public was really quite riled up about this with regards to the fish kills, the water quality problems, who's causing it. And you can see down at the bottom there, the farmers are being pointed to with regards particularly the CAFOs. And so our study was intended to look at some of the major causes. It turned out that actually Raleigh Wastewater Treatment Plant was a major player here. So upgrading that was pretty important. So even though this is about 180 miles or so from the Neuse estuary, these wastewater treatment plants, notably Raleigh, were major players. A big municipality discharging into the Neuse. But also there were concerns with the concentrated animal feedlot operations. And all of you know there are a lot of them in North Carolina. There are a lot of hogs. They are zero discharge operations. So the way they operate right now, and I know Mike Williams has been working on this for years, but they have lagoon treatment of the liquid that comes out of the hog pens, and then they are to spray the liquid at agronomic rates onto fields. Agronomic rates determined by some faculty here. They are zero discharge operations. So it was difficult to factor them into the analysis when we were doing this study. And one thing I want to emphasize here, I'm not going to go into any detail on this, but one thing I want to emphasize here is that this science is really complex. As a physics major, as an undergrad, it always bothered me it still bothers me when someone says, it's not rocket science. Well, as a physics major, I can tell you rocket science is complicated, but the uncertainties aren't that great. Biological, chemical, ecological science in the real world is complex, and the uncertainties are huge. And this is something that I grapple with in most of my modeling work is how do we deal with the uncertainties? How do we quantify the uncertainties? How do we make decision makers and stakeholders feel they're better off knowing the uncertainties instead of giving them a prediction from a model of what's going to happen with no uncertainty. So this shows you a very complicated process. It was really hard to figure out what happens with that nitrogen. We know it's on the agricultural lands. Where is it going? Is it staying there? Is it volatilizing, going to the groundwater, or going up in crops that are harvested? Complex. It's just not that simple. And yet we have to make decisions on that. Okay, one thing that we do know works, and I'm pleased about this, and back in the about 15 years ago, I chaired the Neuse buffers panel. We had a great group of people, many NC State scientists coming and talking to us about the importance and nature of riparian buffers. Wayne, you may have been one of the people who came, certainly Wendell Gilliam. And so we established the nature of the buffers that had to be on all of the streams, and the EMC approved it. Much to initially my dismay and then delight, someone proposed a drastic reduction in the buffers as legislation in the General Assembly, and fortunately it didn't see the light of day as a new rule. But unless you can challenge this science, I can't imagine anything else. This was done very thoughtfully and thoroughly. Okay, with regards to the Neuse, we got the TMDL, 30% reduction in nitrogen load. Chris Ressler, who was my student at Duke many years ago, who was the scientist with a Division of Water Quality, was a key player in getting this approved by EPA and implemented, and things are not terrific, but they're much better on the Neuse. So I want to end with a couple of challenges and issues. Pharmaceuticals is one of the things that I know a number of you guys, these scientists here, have looked at here at NC State and at Duke, and probably most of you have read about the pharmaceuticals that we use either over the counter or prescription that go through us, through the wastewater treatment plant, and are affecting aquatic life. And that's a tough one. It's sort of like the synthetic organic, well, it is synthetic organic chemicals that we have concerns with in drinking water treatment. There are many of them. There are many possible effects, and so we're gradually, slowly getting a handle on that. Small dams, I know that's a concern to people here. And finally, in-lake treatment versus pollutant load reduction. So just quickly on the small dams, there are about 1,200 high-hazard dams in North Carolina, and those where, distressingly, loss of life is likely if the structure fails. Now, there are people in DEQ, in the Department of Energy, Mineral, and Land Resources, that have inspection responsibilities for over 2,600 dams, but limited staff, and what they do is inspect, and then it's the responsibility of the dam owner to take care of things. So the advice is if you live down gradient from a small dam, to some degree it's your responsibility to be aware of what's going on in the safety of the dam. Okay, and then finally I want to talk about this item. The SolarBee. I've written a couple of op-eds about this with some of my colleagues at the universities about this, and had some not so positive things to say about this. Probably all of you know these are in Jordan Reservoir right now, and there's talk about putting them in Falls Reservoir. They are solar run, see the solar panels, stirrers of water. And the idea is that somehow these are going to lead to improvements in water quality, such that the costs of the watershed nutrient reductions are not as severe. The reality with SolarBees is that there's no strong evidence that they remove the nitrogen and phosphorus. So if and when you remove them, it's still there. You still have that problem. They don't have necessarily a strong impact on algal levels. They have been shown to impact the harmful algal bloom species. But are they going to, the issue is, if they aren't affecting the nitrogen and phosphorus to any degree, do you have to leave them there forever? I haven't heard any answer to that question. And if you take them out, we're back where we were before. So this, quite frankly, is a stopgap measure, in my view, that is costly and having very little positive impact on what we're trying to achieve in Jordan Reservoir. And with that, I'll stop.
Thank you, Ken. Following the same procedure that we used before, we can take one question. So if someone has a burning question, we'll be able to take that now. We'll have someone bring a microphone to you.
Yeah, you want me to comment on that? Yeah. You know, from the thinking about protecting more waters, it makes sense. Expand the waters to these other water bodies that currently aren't considered navigable. The concern that I have about this, and I've talked to some of my colleagues, including some at DEQ, is that if you're not increasing the resources in North Carolina, let's say, to monitor compliance with the water quality standards, if you're not increasing your monitoring program, basically what you're doing is spreading out your monitoring time and dollars to more miles of stream or whatever the water bodies are. And if one might argue that the navigable waters are the larger waters and the ones that perhaps are more important for aquatic ecosystems and human use, you might not want to spread that out to the waters that currently aren't listed. I know that's controversial. I know the ephemeral streams and the small streams are playing a role in contributing to the larger streams, no question about that. But I'm worried that the resources are not going to be expanded to maintain the same intensity of monitoring. And I've asked people with DEQ, and they've quite honestly said to me, you know, we're probably just going to keep monitoring what we monitored before. So it's not going to really have any change. The only way it can really have positive change is increase the resources for monitoring to cover that.
Thank you again.